So when we ask the question, what is the role of AI in biomedicine? I don't think we can ever really think about AI as an oracle. I'm not one that believes we'll ever have a perfect model. Long time. In the last handful of years, this has really fundamentally changed. Let me that really have enabled this acceleration in the last, I'd say, 8 or 9 years. The first of these is new mathematical ideas of attention. Listening to the talks today, I know many of you work directly in the space, but if you think about it for a minute, the ability of a transformer or related methods to actually allow a machine to take an enormous context and focus on only the things that matter is a fundamental breakthrough that has allowed us to actually have machines that learn very, very rapidly. And this paired with self-supervision leads to some really interesting breakthroughs. Specifically, it means that we no longer are limited to training models based off of data where we have labels, because of course, getting high-grade labels is very expensive, it's slow, and that means the data sets are small and the resulting models are very brittle. You all know what self-supervision is. It's about predicting the next word in the sentence. In the case of language, I will tell you, it was very surprising, I think, to many of us, just how powerful this was. And the best analogy that I've heard from this is actually from Elias Suskabar, who made the point that if I gave you all but the last page of a crime novel and then asked you to complete the sentence, and the killer was, your ability to predict that next word is not just your brain's ability to do information retrieval. It's your ability to link together concepts in that novel, link it back to your understanding of how the world works and how crime novels work, and actually make a probabilistic assessment of what that next word is. It's a very, very powerful idea. But of course, that only works when you pair it with scale. That doesn't work if you train a model to predict only the next word of a sentence. You really have to be able to have a model that can think about a whole novel in that case. And one of the most important breakthroughs was these observations of the scaling hypotheses. And that's just the idea that more is better. More data, more compute, more parameters. And really, really practically and importantly, the ability to predict these scaling laws means that investors are willing to put more and more money into these things. Again, both from the pure infrastructure layer, but also from a modeling perspective. Now, I first put together this slide last year when I gave a talk to a bunch of cancer biologists trying to explain, like, what is it about AI? Why is this different? I do think I have to update this now. I think there's 2 more things that have really emerged in the last year or so. The first is this idea of test time compute. And that is just the idea that spending more time on answers is a new scaling law. You know, the analogy here is there's a set of questions you could ask me in the Q&A, and I could spit off an answer right off the top of my head. But there's another set of questions you'd ask me that I would really have to go think about it for a bit. I might write down some thoughts, I might iterate on it, I might write down an outline, and so on and so forth. And you can get these models to do the same thing. And then finally, agents. And this is really the ability to decompose tasks and then also act in the world. And I'll come back to that in a little bit. So what do we mean by reasoning? Do you remember the first time you played with ChatGPT back in December of 2022 or maybe GPT-4 in March of 2023? Here's one of the first queries that we tried. And the idea was, can you actually get this language model to work in a clinical context? This is a made up vignette drawn from a licensing exam, but basically you're giving ChatGPT a quick synopsis of a patient. And what's really remarkable is it immediately zooms in on the important pieces of this little vignette, pulls out a differential diagnosis, suggests the tests that you can order to actually get to distinguish between these two, and even suggests a treatment plan depending on what the results are. Now, in this particular vignette, I went ahead and said, great, I ordered those tests, I got back the results, and I have this really great conclusion, which I'm told, I'm not actually a doctor that knows these things, but I'm told this is not the right answer. And what's really, really, really remarkable is, as polite as ChatGPT is, it still sticks to its guns. It tells me, no, 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 your answer is wrong. Here's a more likely answer, and if you don't believe me, here's some more tests that you can order. If you think about it, I certainly did not think that we would be at a stage where we would have AI that could do something like this. Now, how do you actually measure how accurate this is? For a number of years now, we've been using the US medical licensing exam as a baseline. We have these specialized models that were getting better and better and better over time. as soon as the GPT class of models hit, this just really exploded. And at this point, these models are essentially saturated. This particular analysis goes up through O1. The O3 model, I think, is still being run, but it's even a little bit more. But at some point, I'd argue that you've hit the limits of what you can measure in a multiple choice exam. Of course, multiple choice exams are not the be all and end all. I think one of the most interesting studies that's been ongoing right now is a live working paper that keeps getting updated periodically, is really led by a team at Harvard and Stanford medical schools, by Adam Rodman in particular. And the idea here is, how do you go through whatever data sets we have, where you have complex diagnostic challenges, how do you turn those into evaluations for both computers and machines? And then how do you have separate panels of experts that can actually evaluate the quality of these? There's a number of examples. I'm not going to belabor the point too much, but at this time last year, the big take home was that GPT-4 was already on par with human doctors. Of course, O1 came out 2 months after this press release and is blowing both GPT-4 and those models away. There's other examples here where we continue to see these models getting better and better. And maybe the most interesting one, just from a practical perspective, is this last one, which is using AI as a second opinion in an emergency department. And I like this because you're not actually dropping in and asking the AI to make decisions. You're asking it to, in real time, double check the triage, double check the emergency room decision, double check once they're back in the ICU. And just to read off the current conclusion from the authors, that these LLMs have achieved superhuman performance on general and medical diagnostic and management reasoning. What we really, really, really need is prospective human trials to understand how would you actually integrate this into practice. But I still don't find these super compelling just yet, because they're still giving AI the whole picture. And as I just said, the science and practice of medicine is iterative. Nobody walks into their physician and has everything scanned, unless you're one of those billionaires that do that from time to time, because you can. So the question really is, can a language model reason under uncertainty? And critically, can it ask the next important question? So one of the things we've been working on is this very question. First, how do you even make a benchmark around sequential diagnosis? So this is a working paper that's under review now. We just posted this a couple weeks ago. And the idea was really to use the LLMs themselves to create their own benchmark. And it's a straightforward example here. Here we're taking the New England Journal of Medicine CPC reports, where you have the full workup case history that's published, and you put it into an agent. In this case, it's run by OpenAI's O3 model. And you say, okay, you are an oracle. You have all the information. You're only allowed to give precise answers to precise questions. And if somebody gives you a question where you don't know the answer, well, you have enough context where you can make up something that's plausible sounding. So that's the basic setup. Now you can have other language models or humans actually test the system and ask questions. And once the human or model comes to a conclusion, they can give an answer. And then again, you can ask the AI agent to actually, or a judge agent to actually measure the results. We've done a bunch of human evals to be sure that all this stuff makes sense. But the upshot of it is, once you do this sequentially, now you can measure not only diagnostic accuracy on the y-axis, but somebody's asking questions and they're ordering tests. And so you can actually measure the total costs, for example, of the medical tests. So these are things like, the pathology or the blood work. And so what I'm showing here are the red dots from various physicians. You shouldn't be surprised that doctors are only 20 to 30% accurate. These are really hard tests that are published because they're really hard. They're designed as diagnostic puzzles, so take that with a grain of salt. But what's remarkable is pretty much every language model we can get our hands on off the shelf is at least as good, if not substantially better, than humans at these tasks. Now, this is all still theoretical. I think the most important question is, how do you get AI into the clinic? And what would that actually look like? And I will say that it already is in the clinic, but not for doing things like this just yet. I think one of the most interesting things that's happened in the last year or so is on the administrative side. So if you have an AI that can automatically take concepts out of a note, you can also have an AI that can take concepts out of a patient physician conversation and then structure that into administrative artifacts. And this turns out to be profoundly useful. There's a couple of Microsoft is doing this. There's a company called Bridge that's doing this. It was just valued at, I think, $5 billion. This is really taken off. And what we're finding is that it's saving as much as 5 minutes per encounter, which if you're a primary care provider that sees a couple dozen patients, this really, really adds up over time. So what I just showed you is that these general purpose models have already learned, just from essentially reading the internet, a lot about medicine, which is super impressive. But what about all the things that are not on the internet, that are not already known? How do we get these models to learn? One of the most important ideas that's been around in medicine for a while now is how do we actually learn from real world data? And I will tell you, if you take 1 million, 10 million, 100 million patients records and give it to GPT, you're not going to get anything useful out of it, right? So the question is, how do you actually use these AI in a very useful way? And one really striking observation is you can simply use these language models to structure that unstructured information. So take all the EHR data and simply put it into the structured tables that we know and love. Once you can do that, you can do things like patient-like mind reasoning, you can do clinical trials matching, optimization, so on and so forth. We and others have published on this. The point is, you're not using AI to learn directly, you're using AI to actually supercharge the machine learning and the stats that you know and love, right? And this operates at 2 levels. One is it allows you to take what humans are already doing and scale it to more records, but it also allows you to scale it breadth-wise too to more features as well. Now, once you have this, once you have your data in a structured database, now you can also use this at runtime, where now if you ask a query, you can actually use the GPT to go in and query the database, pull that back into its context and give it the answer. This is what we call RAG, retrieval augmented generation, is used all over the place. Typically, this is used actually by essentially like an internet search query where you're doing a vector compression of the data, but you can use this into a clinical database. We just had talks on rare disease. I've seen this used, for example, for ClinVar, so that when you type a query and it'll go off and actually pull off structured information on the actual variants. Now, this is really, really good for local Q&A, where the answer you're looking for is a fact, if you will, either a line item in a table or embedded in a sentence in a document. It breaks down when you're trying to do global sense making and say, in a scientific domain, what's the latest on such and such a theory? And this is where ideas like graph RAG come in. And the idea here is that you can actually use either a pre-constructed knowledge graph, or you can get the LLMs to automatically construct a knowledge graph by identifying entities and relationships between those, and then automatically summarizing documents in a hierarchical nature, so that when you go to ask the query, it can actually traverse the graph and really start making connections across documents in really, really interesting ways. This is really an area of active research and has exploded in the last maybe 12 or 13 months. But of course, medicine is about more than text. It's really cool that we can have an AI that can summarize the information that a pathologist wrote down in their pathology report. But of course, that's a human writing down something from an actual image, and same with a radiology image. So the next question we might ask is, can we use the same ideas that were used to train these language models and get them to learn imaging models as well? And of course, this has been an area for a long, long time, but just in the past year, we've seen an explosion of work in this field. So one of the things that my team has worked on is with pathology a lot, and one of the things that we found is, yes, if you just take a model with the same basic attention mechanisms, you have to be a little clever because these are really, really big images, and the same basic ideas of self-supervision, you can actually train these foundation models very, very rapidly, and they're able to detect cancer as well as humans, and especially better than humans for rare diseases where there's limited training data. They can also start to detect biomarkers. We're seeing similar things with radiology. This is one of my favorite ones. If you think about an image, especially in radiology, all that is a 2D projection of a really complex signal. So why would you have your AI focus on the lossy 2D projection of pixels when you actually move upstream and think about the raw signal? So one of the things we've been doing working with Siemens is how do you actually pull in raw signal, train a foundation model at that level? And once you do that, you can get these really profound denoisers that allow you to take these low signal to ratio images and move them into what we think is clinical grade images, although that validation is ongoing. So a couple points here. One, these models are not always all the way there. Oftentimes you have to fine tune those. So this is something that was just published a week or two ago off of our pathology model. And what was cool about it though, is it showed how you could take only a few thousand examples. I think this was with EGRF, and fine tune a base model that was trained on, I think it was about 1 million images. And so very quickly you get a model that is good enough at predicting the particular biomarker that you could save order of magnitude 40% of genetic tests in a clinical setting. The other observation, I think this is important, not just as a tech company, but for users, is that as these patterns get repeatable, and we start just turning the crank over and over again, that provides an opportunity for the tech company to start building products. And it's still super early days, but what we're starting to see as a result of this is it becomes very easy for us to get models into the hands of the community much more quickly. And of course, Hugging Face has been leading in this, and it allows the diffusion of this new technology to happen very rapidly. But the third point I want to make is that it's not all about models. In fact, models oftentimes are not the source of the problem anymore. So I just showed you an example of AI operating on pixels. Of course, we've been doing this for years. I think there's on the order of about 150 FDA-approved models for radiology. I also just showed you a model that operates upstream on the raw signal. The problem is I don't have a way to get this into the clinic because this part of it is actually in a closed system, right? And so there's things that we're doing right now in terms of actually shunting the data off of these systems into the cloud so then you can operate on it. But the point here is really you have to think about this end to end as an ecosystem. Oftentimes the models themselves are not enough. Now, another thing you might ask is rather than just using AI to actually get to a answer or detect a feature, can you actually use AI to generate the actual report? And this, of course, gets us into multimodal AI. And we've heard some talks about this before. I'm not going to get into the details, but I think the key takeaway here is that we're now at a point where if you have a pre-trained language model and a pre-trained imaging model, it actually takes a very small amount of data and frankly a very small amount of compute to actually align those two models together through just training things like linear adapters or simple multi-layer perceptron adapters. And the result of that now is you have really pretty magical experiences. So here's an example that we published last year. I think just a couple months ago we updated this to 3D images as well. But it really allows you to ask questions of your images, but also to show what the model's seen. And in this case, this is about really object detection and object parsing in real time. You can also then use this to do things like write reports and do so in a grounded way so that the radiologist can actually validate the findings that it's writing out. Again, these are early days. These are still not yet used clinically, but this is something that we're working on really with a couple of partners in the provider space to figure out what is actually the place where this becomes useful in the clinic. I'd be remiss to point out that proteins are languages too. This is something, I think we heard a little bit about this earlier in the case of DNA. A couple years ago, we showed how you could use diffusion model, as in the DNA case, to train protein language models as well, or protein diffusion models. And the important point here was that while there's lots of work that's been focusing on structures, there's orders of magnitude more sequence data than there are structural data. And so if you spend a little bit of time getting a model to actually think in multiple sequence alignment space, you can actually get a model to automatically learn the concepts of structures. In this case, the animation that's playing right now is taking out an actual motif and then asking the model to fill in the details and hold the motif structurally sound while coming up with new scaffolding. Again, the model's never seen a structure before. It's just doing this by pulling out the concepts from the sequences. I think it's posted today, but sometime, give or take today, we just posted an update of this where we actually said it was great that we could do this with a diffusion model. That was a lot of work. We threw it all out and we said, let's do it all with a language model. And the reason to do that is once you do it as a language model, now you can actually scale the training data. You can focus on the training data and go from a few million sequences in multiple sequence alignments to, I think this was about 3.5 billion sequences that are both aligned and unaligned and singletons. And you have to be a little clever because proteins are not left, right, autoregressive, but there's tricks that you can use, and then you can leverage everything that we know about language models and how you train them to really turn that crank very rapidly. I'll also point out, just as a little preview of the future, once it's in a language model, it becomes much easier to start pulling in other modalities in a very native way. I'm not going to talk about DNA, molecule, cells, et cetera, but this is clearly, I think, where the field is going in the next couple of years. Now, there's a special case of synthetic data. We heard a little bit about that earlier, but I want to zoom in on another example, which is the special case where we actually understand what's going on, which typically is not true of biology, but it is true of physics, and it is true of some chemistry, right? We understand quantum chemistry. We can write down those equations. We've been able to do so since the 30s, but it's really, really hard to simulate it. But we do have simulators, and what that means is that you can effectively give yourself a source of infinite training data. So I'll give you just a couple examples here. And again, the idea is that we already know how to simulate it. The problem is it's really, really computationally expensive. So rather than using the simulator to get to your answer, use a simulator to give yourself training data under the hypothesis that the AI algorithm will be a heck of a lot faster. So one example we just published, I think 2 weeks ago came out, is this idea called accelerated molecular dynamics. I'm not going to walk through this super busy slide, but the idea is we literally just took the architecture from AlphaFold. We added a diffusion model onto it so you can actually get distributions. But the really interesting thing is more on the training data here, right? So we started with the AlphaFold database, exactly what's been around for a while. That doesn't really get you anything dynamic. You can sort of fudge it with a diffusion model and whatnot. But what you can use is you can use off-the-shelf molecular simulators to take a structure and then sample the whole space, or the whole conformational space around that static structure, tie that back into the diffusion model, and now you actually have a rich representation about the equilibrium distribution of that molecule. And of course, while you're at it, you might as well add some published or some structural data, some experimental data. So once you do that, now you have a model that can take a sequence and not just get you to a static structure, but you can actually, through the diffusion model, give yourself a equilibrium distribution of the structures that could be formed. That allows you to do things like identify cryptic binding pockets, look at local unfolding, look at domain rearrangements, and even estimate the relative free energies, which are proportional to the frequency with which any particular conformation shows up in that distribution. You can push this even further if you go down into the quantum chemistry space. So if you're familiar with quantum chemistry, which I will say I'm not, one of the core ideas is we actually know how to, again, write down the equations. This was Schrodinger's equation back from, what, the 30s? The problem with Schrodinger's equation is this exponential in the number of atoms, which is very, very large. And so DFT allows you to actually estimate that. In fact, it's an exact representation. It decomposes this down into a cubic formula. The problem is that red thing there, the exchange correlation, we don't know what that is. So we can model everything but the exchange correlation function. So for the last 60 years and at least one Nobel Prize, folks have been focusing on how do you actually get exchange correlation functions that are reasonably accurate and reasonably computationally efficient. At this point, there's over 150 different exchange correlation functions that are used in different contexts. What we did was said, well, great, let's take all that expertise and let's just bake that into a deep learning algorithm. And we're going to spend all of our computational resources just on generating those synthetic training data. And once we do that, now we can train a single shared model that essentially is integrating over those different exchange correlationals. This is early work. There's a long ways to go on it, but we're already starting to see signs that this is starting to work really well. It's a really interesting paper, and even better, the explainer videos that come along with it to explain quantum chemistry in a way that I couldn't possibly explain. I'm going to make one more link here, and that's what is the future of quantum? So this is actually coming. We have quantum computers at work. We have this chip here, the Majorana chip, is scheduled to be released for public use in the coming months-ish. It's still small. I am very confident that the first useful applications of quantum computers are going to be precisely this. It's going to be generating training data for AI algorithms for computational chemistry. And for no other reason than very few people will have access to the chip, so it's a good way to extend the technology. But again, once you get to these AI algorithms, what we're finding for both those other two papers is what you end up with is something that's as accurate as the exact simulation, but between 4 and 5 orders of magnitude faster, and in some cases can actually generalize a little bit further. All right, so collaboration. So we have models that understand the general domain just from reading the internet, essentially. We have models that can now learn from new data. And as I said, we have the ability to map all these models into a language space, which means that we have models that can actually talk to not only humans, but can talk to each other. And this, of course, gets us into agents. And there's lots of ways we can think about agents. The way I like to think about it is really as a new programming paradigm. And at a very simple level, what is an agent? It's simply an LLM that can take instructions and can use some tools. And the ability to use tools is very important. And the ability to instruct each individual agent to do something different is very important. But at the end of the day, once you have this, all you need to do is hook it up to some input and some output, and you have an agent. And where this becomes really interesting is when you actually connect it to some intelligent way to actually orchestrate these, and then, of course, to interact with the humans. So when we first started digging into this in the medical context a few months ago, maybe a year ago or so, we were thinking, what would be a place to really tie together all the work that we've been doing, just as a demo of what would be possible, really to get the medical community thinking about agents and thinking about where this would go. And the example we came up with was a molecular tumor board, right? And if you're familiar with molecular tumor boards, or more generally these multidisciplinary conferences, so where you have complex cases and you pull together sometimes a dozen or more specialists to actually reason through this particular patient's case to figure out what is the right course of treatment. So if you think about a tumor board, what are the agents that you'd actually want engaged here? Well, you probably want a patient history agent because the actual EHR is a mess and you want to structure that into a patient timeline. You'd want an agent that understands radiology, which I already talked about, one that understands pathology, another one that understands cancer staging. So this is actually devilishly tricky. The cancer staging manual runs some 1,200 pages or so, and it's all in text. And also, even if you know that, even if you write down the rules, to pull that information out of an individual patient record requires going across longitudinal timelines for the EHR, et cetera, et cetera. You'd want an agent that can understand the literature, so where those graph rag approaches that I talked about before are very, very powerful. You'd want one that can map clinical trials, say, okay, for this patient, given the features that I pulled out, let me just go ping clinicaltrials.gov and see if they're eligible for any clinical trials. And while we're at it, Word and PowerPoint are programmable, so let's have an agent that can actually create the documents for us. And how would you actually integrate? Well, we're Microsoft, so we're going to tie it in with Teams where people are already talking to each other. So what does this actually look like? Here's a demo we put together. We tested this out now with Stanford Medicine and have started exploring this with a number of others. But this is just in Teams chat. There's agents here. There's actually humans as part of this particular chat, although I think this vignette is only agents. So we ask, hey, Biomed, I'm going to be doing this, this tumor board. It puts together a plan. I say, that's great. Here's the patient that I actually want you to go pull the information from. And it's going to go off and start doing its thing here. So the first thing it's going to do is ask the data organizer to pull together the timeline. Again, this is automatically structured from a unstructured EHR note. Of course, you can ground every one of those statements, so you can click on it, and as a physician, I can go back and see what was the actual highlighted part of the report that got me that claim. Here's going to look in at the actual treatment plan that was given, that's in the EHR record. Let this keep running here for a minute. I think in a second it's going to pull up, ask the radiology agent to do some work. Yeah, here we go. So the radiology agent is going to call a couple different models to get some initial estimates of the CT volume. The pathology agent here is going to say what it's seen. The patient status one is interesting. It's actually coming back and saying, hey, I'm missing some information. Can somebody go fill this out for me? And the data organizer agent is now going to go in and actually pull in the missing information. And now here we have the treatment agent that's actually going to go actually recommend a treatment plan anchored to the guidelines and showing where that's coming from. I forget what comes next here. This is a little bit of a surprise. Oh, yep, here's the clinical trials agent now that's gone ahead and dived into clinicaltrials.gov and identified a trial that's ready. And then I think this last one is going to actually write up the report. Yep, there's the actual document. So now we can click on the document, and this is a much fancier Word document that I would ever personally write. But once you can code, then you can make this look really good. And of course, then you can automatically go and create the PowerPoint as well. So you can imagine this, of course, gets clinicians really excited. This is probably the part of the talk where I have a whole bunch of clinicians say, hey, can I have this? Can I have this? Can I have this? So we're working on this. But I would say that one of the important points is not just the demo. Like Microsoft's not going to go make a molecular tumor board product. It's more about the concept. What we've just done is we've enabled us to have every one of those agents is itself a publication. There's a lot of work that goes into that. But it allows you to decompose this problem. You can have different researchers focusing on different parts of the problem, and then in a very, very simple way, actually stitch them together into really interesting interactions. Now, there's a lot of open questions here. Some of the open questions are around verifiability and error propagation. What happens when you have an error in one of those outputs that then gets interpreted by another output? There's regulatory questions. What happens when one of those agents, actually the pathology agent, that I think this one was using, is actually FDA regulated? And it's not at all clear what happens if you have a model that has an FDA regulated output that then gets reinterpreted by another model. So there's a bunch of things to work through here. And frankly, I think a lot of the work is really user research that has to be done to understand how would physicians actually use this in a productive way. Because what we don't want is I'm just taking a step back and just following whatever said, but we really want this to be part of a dialogue. So the last point I want to make here is that intelligence also emerges from collaboration. So I just showed you an example of tool use, and it's pretty obvious, I think, about how that allows you to integrate a lot of different sources of information. But I think a surprising thing for me is just the fact that you can collaborate it by itself actually raises the intelligence of the system. So let me close by going all the way back to one of the papers I showed earlier, which is the sequential diagnosis paper. The point of that paper was not really just the evaluation. The point of it was actually that you could come up with an agentic system to solve this problem. And the idea here is that you can take a language model. In fact, you can take any language model, and you can compose it into a set of, in this case, 5 different agents. These circles up here, and apologies, they're small. But essentially what you do is you just prompt them all differently. So the one in the upper left, the pink one, is the hypothesis agent. And you simply prompt it and say, hey, as we go through this process, I want you to keep track of a Bayesian probability distribution of what the five most likely diagnoses are. The next one is the test chooser agent, and you just prompt it and say, hey, based off everything we know right now, I need you to list out what are the top 3 tests or questions that we should order or questions that we should answer. You have the checklist agent, whose goal is to just basically ground and make sure that we're not just making stuff up and that anything that's said is actually anchored in some sort of reality. You have the stewardship agent, which is interesting because this one does have access to a tool. It's saying, okay, for any test we order, what's the cost of that? And let me just ask the question, is there something else that we could order that would get the same information at lower cost? And the last one is maybe my favorite, is the devil's advocate agent. And we've actually seen some really interesting cases of this one where All we're doing is prompting. Again, it's not a special model. We're just prompting it and saying, hey, given the conversation that's going on, ask the question, are we missing something? Are we getting to group think? Let's think outside the box here. And there's some really interesting anecdotes that come up with that. Now, as that set of agents is collaborating, we basically ask them to get to consensus to either ask the next question, request a test, or say, nope, we're done, we have a diagnosis, and then we proceed from there. And what happens, what we see happens is if you take this original plot that we showed, and we put the O3 model into this, all of a sudden we get a massive shift up and to the left. We're running this, there's a series of plots because you can tune this in different ways. The one box is really the sort of just let it go. And you end up with a little bit of a performance boost. This is relative to the O3 model, so it's maybe a 4 or 5% point boost. But you actually end up with a much cheaper model because essentially as it's going through, it's reasoning, hey, I can get to that same answer with a lot fewer tests, and in this case actually be more accurate. But you can also then tune this and give it a budget, and it ends up cheaper as well. But what I think is really interesting is this boost in performance happens with whatever the base model is that you give it. So you can give it Grok, you can give it Claude, you can give it even GPT-3.5, I think it's in there. Maybe that's not in this one. But all these models, as long as they have enough capacity, once you get them working together, their intelligence boost, if you will, actually bumps up pretty substantially. And again, this is demonstrating this test time compute idea that I showed before, that it's not just about the power of the model itself, it's letting the model actually think through a problem, and decomposing the problem into these agents is a very simple way as a programmer, if you will, to actually get it to do this test time compute. So let me close with this. When we talk about intelligence and model intelligence, I like to think of the intelligence stack, and that's really three things. The first is models, and that's what are the general domain models, it's what are the special models. I think over time we're going to see these highly specialized models collapse into fewer and fewer domain models, or fewer and fewer generalized models, but we're still in a world where there are many, many specialized models. On top of that is agents. Again, this is how do you have these models work with tools, but also how do you have these models reason about a problem and think together, think collectively about a problem. And on top of that is the ecosystem in which these sit, because if they don't sit within an ecosystem, they're not useful at all. And this is everything from what's the data that they're coming from, what are the processes they sit within, how do they actually interact with the humans. And with where we sit right now, these are largely decomposable. So you can actually work right now with agents, with existing models, and use them with really very little amount of compute or effort to actually supercharge the general purpose reasoners, to orchestrate tools, to leverage domain knowledge, even while the models underneath start getting more and more powerful. And as those models improve, of course, we're going to have better tools, we're going to have better use of data, but I also think we're going to start seeing a realm where these models more innately understand biology will actually lead to better reasoning models as well. Right now, we're stuck with asking, say, a general purpose model like GPT's O3 to reason about DNA. It's not going to get very far. Once we get better and better models that more innately understand DNA, I think we'll get better agents and reasoners for that as well. And of course, the ultimate question is, what are the scientific problems we're trying to answer? What are the data experiments? What are the workflows? And ultimately, how do we empower the scientists? So with that, thank you again. I'm happy to take questions if we have some time.
Thank you very much for that very comprehensive and inspiring talk. I think there will be plenty of questions.
Hi, thanks. Lots of really exciting stuff there. I mean, I found the results with the diagnosis problems very impressive, but presumably we don't know whether ChatGPT was trained on those problems. It could have had those problems in its training data.
It's a super important problem or question, and I would say it's getting harder and harder to do good science for that reason. In this case, we've actually been partnering with the New England Journal to do some of these. So these are the CPCs, what is that, clinical pathologic case studies. Those are published every single month. And so we actually know the cutoff dates of when GPT was released, the versions that we're using, and then we can do validation on ones that are after. I will tell you though that if you compare, before and after, you don't see any difference in performance. And in fact, there's a general observation here, which as these models get bigger and bigger, the difference between validation and training performance seems to be collapsing over time, which is a good thing. It makes our life easier, but it's still a very important question. And I'll say, just to add to that, it makes it really hard to evaluate humans too. I think The results I gave you, we didn't let humans use tools, which of course is not realistic. But the reason is if you use Google, even just a couple of searches will get you those case reports. Will pop up. And so we're isolating that. We're running that right now. But.
Also, I mean, you mentioned in your title mentioned general AI, and I wonder if are you actually working towards that? Is that important for?
I was doing a bit of a play on words here. I was saying general AI, not artificial general intelligence. So what I mean by this is really the fact that we're seeing a collapse of methods into the same tools, and we're seeing increasingly one model that can do many, many, many things. Now, do we want to call that AGI? No, we're not there yet. But to me, what's more relevant is the fact that we have these set of tools that we, as a practitioner, you don't need to go train a language model. The whole field of natural language processing used to require a huge amount of expertise. And all of a sudden I have this general purpose model that I can just prompt and go off and do things. Not everything, but I can go off and do really important things. So that's really what I mean.
Great, thanks.
Thanks, Jonathan. Great talk. Just have one question, I guess. I mean, what you presented looks fantastic for the future. If you want to put this into practice, as you know, as a lot of healthcare systems, particularly in clinical practice, they still have a lot of legacy systems. Some of them, they're probably not even accessible, apart from even most of them still on-premise, not even in the cloud. So how's Microsoft is thinking about
so just to the question, this is back to the ecosystem question, right? It's great to have a model. If you can't access the data, it's not useful. So a couple things. One, on the good side, there's been a massive shift toward digitization in most, but not all countries, but most European and North American countries. That's clearly not enough. I will say some of the most intriguing applications for this are specifically at the data interop level. So having agents that can go off and actually do the fire service call and structure the information, which is tedious. Having the agents go off and do prior auth, for example, which is a whole stream as well. That said, I think what's better is when this actually gets more deeply integrated within the actual, not just EHR systems, but the PAC systems for the imaging, et cetera, et cetera. So that is coming. It's slow, but the fact that we have ambient clinical intelligence is already being used by millions of doctors, there's a clear value prop right now that's driving demand in a way that you typically don't see in medicine for new technologies. So I'm hopeful it will roll out quickly, though. It's an important question.
And for one more question.
I love the way you're thinking about this and the confirmation that you gave about the value that us physicians provide. A lot of times the medical decision making isn't as higher order at a certain level of training as people think. It's more about getting the information you need. And you sort of confirm that there. But in terms of thinking forward about how to structure data collection in a way that we can extract even more insight, can you envision a world where the AI will both capture audio and visual of a patient encounter and extract information from that, so that way it can ask the right questions, read up on facial cues, voice inflection, et cetera, et cetera?
Yeah, no, it's a super interesting point. One of the things that makes ambient clinical intelligence really interesting is as a new way to collect data. So this is the idea that you're actually recording the patient-doctor interaction. Right now, that's being used to reduce the administrative burden for physicians and make it so the physician can sit there and talk to the patient instead of sit there talking to the computer. Once you do that, you are capturing that audio stream. And in fact, this is something that a number of these companies are starting to do, is actually turn that into an extensible platform where others can drop in a model and say, hey, I have a voice recognition model that the recognition is detecting certain types of diseases. In principle, could you add a vision to that? Sure. I wouldn't be surprised if that comes at some point. In principle, you also now have a plug where the system can start recommending the questions that you should ask. I think a very interesting one to start comes back to the prior auth of, hey, before you do this for this patient's insurance, you need to order this test, or you need to ask this question, or let me help you do that work, basically. I think there's still some basic user research questions about how do you surface those questions to you, the physician, in a way that's not super distracting, that doesn't interrupt the conversation. I think user research is as important as any research in the space right now, because we just don't know how to do that well.
Thank you.
Thank you all, and thanks. Was there one more question? Okay.
This is the end of the day, right? We can go as long as we want.
Yeah, thank you very much. Very interesting talk. I'm curious, like, how do you dealing with the hallucinations of your models, and
Yep.
especially like it's very sensitive areas.
Yeah, so the
And-
question is
yeah.
hallucinations, super important. There's a couple techniques and then a couple maybe philosophical questions here. One on the techniques, one of the very useful things about agents is having them check themselves. It's called self-reflection. And that can actually go a really long way. And that's, one agent gives an answer, the other one double checks the answer of the first one. That's a very simple technique. Another one is through the RAG ideas that actually anchor each example into the source. I think the more complicated question is, what do we mean by a hallucination? And hallucination, I would say, is a probabilistic inference that's filling in a gap. And that often is exactly what you want a model to do. Right? That in a sense is creativity, and especially when we're in a scientific domain, we're wanting it to give probabilistic inferences. So I think a more interesting way to frame that question is, how do you actually estimate the uncertainties in different claims and figure out when do you want to leverage that uncertainty to actually push the scientific question forward versus we need zero uncertainty right now. And the other thing I'd say on this is, increasingly we're finding when you find that the models are saying something wrong, if you go test the physicians, they don't agree with each other either. So then it becomes a little bit of a societal question of, where can we tolerate errors from a machine that we won't tolerate errors from a human, in the same way that we don't tolerate traffic fatalities from self-driving cars, even though they're way lower than human driving cars.
Yeah, thank you.
Thank
Once
you all.
again, and just as a token of appreciation.
Thank you very much.